Welcome to Futures webinar series. I'm Ivana Jevtovic, webinar coordinator. Graphics processing units and their role in modern computing cannot be underestimated. Alongside the central processing unit CPU, the GPU is the primary, enables the processing enormous amounts of data for our modern computing needs. In this presentation, we will take a look at GPU architecture and touch on the various application programming interfaces used to interact with GPUs. We will look at the applications of GPUs, including their role in the computer graphics, as well as the other fields such as machine learning, neural networks, and image video processing. We will discuss IRM Mali, which is IRM's flagship GPU, and Dzanan will share more details about his own role with the IRM Mali team. The speaker on this topic is amazing Džanan Bajgorić. Dzanan is Senior GPU Drivers Engineer at Arm Norway. He graduated from the Faculty of Electrical Engineering in Sarajevo and completed his master's degree in Technical University in Poland. Dzanan became fascinated with graphic processing units due to their application in computer graphics, as well as their massively parallel architecture that enables them to process enormous amount of data efficiently. Dzanan is currently working on the Mali series of graphics processing units and multimedia processors. Welcome, Dzanan, to our webinar, and thank you for being with us tonight. I am giving you a word.
Yep. Thanks, Ivana, and thank you for calling me amazing. I mean, I'm not that amazing, but thank you anyways. Hello, everyone who joined in for the webinar. So, like Ivana said, today we will talk about graphics processing units. Specifically, what are they, how they work, and what do we use them for? So I will repeat some of the things Ivana said for completeness. So we also we'll talk about Arm Mali, which is a mobile embedded GPU designed by Arm. On top of that, we'll also discuss various roles an engineer can take on in a GPU organization, and this should give you a better perspective of various aspects of GPU development and different career paths that you as an engineer can follow within a GPU organization. So GPUs have evolved tremendously in the last 30 to 40 years. Initially, their main and basically only application have been accelerating computer graphics, but this has changed a lot in the last 15 years or so. And GPUs now being used in scientific applications, artificial intelligence, autonomous driving, and much more. For this reason, understanding GPUs and knowing how to program them will become more and more important as the time goes by. So with this in mind, my main goal for this webinar is to bring GPUs closer to you and to try to convince you that having GPU knowledge is an important tool to have in your engineering belt. However, I hope that I will encourage at least some of you to pursue a career in GPU engineering, because honestly, working with GPUs is very interesting, rewarding, and it's also quite a challenge if you like challenges. So with introduction out of the way, let's start with agenda for the day. Okay, so we'll start by discussing CPU architecture. So this is just to give us perspective to understand why we need GPUs. And then we'll switch to GPU architecture, which we'll discuss in some detail, followed by application programming interfaces, which are the way to program GPUs. Then we'll spend quite some time discussing rendering pipeline, which essentially specifies how GPU functions and behaves. Then we'll talk about engineering roles, which is interesting, especially for those of you who will consider working in a GPU organization. And we'll close the presentation by discussing Arm Mali, which is the GPU I and my colleagues at Arm design and build. Okay, so let's start with the CPU architecture. So we'll focus on use cases and limitations of the CPUs. So CPUs, they are designed to execute sequential code with complex control flow efficiently. So at the right side of the slide, you see a code segment with complex control flow, and CPUs are designed to handle such code efficiently. So, like many of you know, CPUs are very deeply pipelined nowadays, and each pipe is very thin, which allows CPU to have very high frequency. So it's not uncommon for a CPU core nowadays to operate at 3 gigahertz, which is a very high frequency. Then CPUs will feature advanced branch prediction, which allows them to hide branch delays. And this branch predictors are so complex that they can take 30 or 40% of the CPU die. Data prefetcher is used to avoid load delays. Essentially, what data prefetcher does, it tries to predict what data CPU needs in the future, and then preloads data from RAM into the caches, so that CPU, when CPU actually needs that data, it will already be in the caches. And finally, out of order execution is used to find parallelism. So what out of order execution basically means is that CPU will execute instructions that come later before instructions that come earlier, as long as they don't depend on each other. So CPUs, like I said, they're optimized for serial execution. They are serial in nature. They have a serial instruction set architecture. So again, on the right part of the slide, you can see a loop. Well, that loop basically just multiplies elements of a two-dimensional array. So this is what we call a trivially parallelizable loop. There's no dependencies in the loop body. So basically, you could run all iterations of this double loop in parallel. However, CPUs, they only have few threads. For instance, Intel's i7 processor, which is a high-end CPU, it only has, even with hyper-threading, it only has, let's say, 16 threads. So there is not enough parallelism to handle such problems. So to get over that, CPUs, like I said, they'll use out-of-order execution and speculative execution to find parallelism. Then architects have extended instruction set architecture of CPUs to include vector and sim instructions, which will also help them handle such problems. But even with all of these things, CPUs still cannot process large data parallel problems efficiently. And that is why we need GPUs. So now we'll talk about GPU architecture. GPU architecture is what is called a massively multi-threaded architecture. And soon we will see why we call it like this. So GPU architecture is based around the idea of SIMD execution. So single instruction, multiple data. So a code segment here shows a simple vector or scalar multiplication. So in this case, vector is 8K elements long, and we just multiply individual elements and store it into a third vector. Again, this is a trivially parallelizable loop. We can run all these iterations independently, and GPUs are designed to handle exactly such problems, so-called data level parallel problems. So data level parallel problem, or SIMD problem, that's a problem where the same operation is performed on many data items. So in this case, multiplication is performed on 8K elements. So GPU processes, let's say, data sets in groups, so-called SIM threads. You may know them as warps. So let's assume for this discussion that a single SIM thread processes 16 of these operations. A single entry within the SIM thread or warp is called just a thread. So if we have 16 threads in a warp, then basically we need 512 SIM threads or warps to process 8K of these multiplications. Now compare this model with the way how CPU works. In CPU, you would need to loop 8K times to multiply all these elements. In GPU, you will spawn 512 warps, and they will do this multiplication probably much more efficient, much more faster than a CPU could do that. So this is this slide shows how are these sim threads or warps executed. It's a simplified diagram of a multi-threaded sim processor. So multi-threaded sim processor, this is a processor that executes these sim threads or warps. So basically within this processor, you'll have kind of a table of available warps. So each warp, it will have an instruction that it runs. Remember, it has only one instruction that runs over multiple data elements. And then it will have a flag that tells the scheduler whether or not the operands are ready. Because sometimes operands might have to be read from the main memory, so that might take some time. So the scheduler will pick a warp that is ready to be executed, and then will execute its instruction across all lanes, all simmed lanes. So sim lane is nothing more ALU, arithmetic logic unit, some registers where the local results can be stored, and a load store unit that can be used to load data from the local memory or from the global memory. And then this single lane is multiplied, in this case 16 times, so that we can execute a single warp out of, so 16 data items we can execute it within one cycle. So now how does a sim thread or warp scheduler picks warps for execution? So essentially, scheduler will pick a ready sim thread and will execute its next instruction synchronously across all lanes. Important thing to note is that sim threads or warps, they are independent of each other, and thread scheduler can basically pick any warp that it wants. So let's say that one warp gets stuck because its arguments are not ready, need to be read from the memory. Scheduler can just pick another one, and so the GPU will be kept busy all the time. Another thing to remember is that CPU threads, they are very heavy. So if you want to switch from one CPU hardware thread to another one, operating system needs to save a lot of state to be able to restart the same thread later. GPU threads, they are very lightweight. So it costs virtually nothing to switch between GPU threads warps. Yes, so let's go. So I said that GPU purchases data in warps. However, this is not how work is scheduled to the GPU. So the work is actually scheduled in blocks, in thread blocks. So thread block is just a collection of sim threads or warps. So let's assume that a single thread block consists of 15 sim threads or warps. So back to our vector multiply example, where we had 8K long vectors, we will need 32 thread blocks to process that vector multiplication. Why is this important? It's important because synchronization can be done within warps of a single thread block. So, for instance, in this example, you can synchronize warp 0 and warp 15, but you cannot synchronize warp 0 and warp 17, for instance. This is because thread block, all warps of a thread block are ensured to be executed on a single sim processor, while other warps of other thread blocks are not. And you cannot synchronize warps that are executing on different sim processors. Implementing that in hardware would be too complex. Okay, so we are now ready to see a big picture of a GPU. Again, on top of the slide, we have this vector multiply example. So this is scheduled to the GPU, where thread block scheduler will pick those thread blocks, and it will schedule them to be executed on these sim processors. In this case, there are 16 of SIM processors within the GPU. A SIM processor has a local L1 cache for itself, so private one, and all SIM processors usually share L2 cache within the GPU, and also, of course, they have access to display RAM, which is just an external memory. So this is a hypothetical GPU. Like I said, it's composed of 16 SIM processors. Each of those processors can execute one warp or SIM thread per cycle, and each of them again has 16 threads. So that means that you have 256 threads that can run in parallel at any given time. Compare this with the 16 threads of i7 CPU. So this is just a hypothetical GPU. A real-world GPU can run thousands of threads in parallel, and they support millions of threads in flight. Note that a thread in flight is not the same as running in parallel. So a thread is in flight. It means that it was created. It's being tracked on the GPU. It's not actually running. But doesn't matter. When you have millions of threads on a GPU, then a scheduler can pick a different warp at any given time, and the GPU will all the time process a lot of data in parallel. And so this is, having thousands of threads running in parallel and millions of them in flight. This is why we say that GPU architecture is a massively multi-threaded architecture. Okay, so another important concept to understand is what we call lockstep execution. So threads within a single SIMD thread or a warp are executed in lockstep. So what this means is that no thread within a warp can proceed to the next instruction until all threads within the warp have executed the current one. Why does it work like that? It's because it simplifies hardware logic for branching control. Essentially, there is no logic for branching and control. So each SIM lane can do two things. It can either execute the current instruction on the warp, or it can be idle. So two SIM lanes, they can never execute different instructions simultaneously. That's just not supported. So this brings us to thread divergence. It's a consequence of lockstep execution. It's a kind of Achilles heel of GPUs. So on the left part of the slide, you see a code segment. So if block will execute if condition is true, and let's assume that it's executed by threads 0 to 7 of a SIM thread or a warp. The else block executes when the condition is false, and let's say it's executed by threads 8 to 15 of a warp. So what will happen is that in the first cycle, basically lanes 0 to 7 will be active, so they will execute their instruction, which is y multiplying elements of y and set and writing into array x. But during that time, in that cycle, lanes 8 to 15 are basically idle. They don't do any useful work. And then in the later cycle, next cycle or later point in time, the first half of the warp or SIM lanes is idle, and the second part is actually executing, doing useful work. So overall SIM processor utilization for this warp is 50% due to thread divergence. So it takes twice as much to process this code segment than if all threads within the warp were executing the same instruction. This can get way worse if you have nested branches. So when programming GPU, you need to think about these things. Otherwise, you will be wondering why is performance so bad. Okay, so the summary. There are a few key points that you need to remember when it comes to GPU architecture. First of all, GPUs are applicable to data level parallel problems only. So GPUs, they have a poor signal threaded performance compared to CPUs. So a CPU thread, a single CPU thread, can be thousands of times faster than a single GPU thread. So that means that GPUs have considerably higher latency. So it takes much more time to process a single operational instruction in GPU than it takes on the CPU. But this is offset by having a huge number of in-flight threads on a GPU that is then used to keep GPU busy. So it's running something all the time and many things run in parallel. So having so many threads alive helps hide the latency of a single thread, and then it makes sure that the peak throughput is reached. And throughput, that's the number of operations or instructions executed in a unit of time, let's say a second. So the second thing to remember is that we need to avoid or minimize thread divergence when it comes to programming GPUs. Thread divergence will most likely hurt performance. So two things that you can do to avoid it is keep control flow simple. Of course, when programs grow more complex, you will need branches in there. But in a sim thread or warp, take the same branch path. As long as that is the case, there's no thread divergence. So GPUs, like we already mentioned, they have enormous potential throughput. If GPUs applied to proper or suitable problems, data parallel problems, they can reach instruction throughput, so the number of operations per unit of time, that is hundreds or thousands of times higher than that of a CPU. So let's immediately move to the application programming interfaces, which are the way, this is the way to program a GPU. So we'll not spend a lot of time here because talking about the APIs themselves, it could be another presentation. So we just shortly talk about them. An API, particularly a GPU API, defines a set of methods and rules for interacting with the GPU. So that's kind of an abstraction that is then implemented by GPU hardware and the driver software. So programmer will use the same API to program various GPUs, no matter how different they may be. So imagine you write the same software, essentially the same software, that will then be able to execute on different GPUs, regardless who makes them. This makes programmer's life a lot easier. So the API will hide the hardware details from the programmer by giving it unified sets of routines to work with the GPU. So on top of the slide, you can see some popular APIs. So OpenGL and Vulkan, those are graphics APIs, and OpenCL is a popular compute API. So graphics APIs define the rendering pipeline to be implemented by GPU hardware and driver software. We'll talk about rendering pipeline a bit later. So it also specifies the interfaces used to render primitives. So the rendering pipeline is, for example, at the bottom of the slide, you can see OpenGL ES 1.0 2.0 pipeline. Don't worry about now, we'll talk more about the pipeline later. Some popular graphics APIs, OpenGL, OpenGL ES, which is OpenGL version for embedded market, vertex, Vulkan Metal, and there are some others, but these are the main ones. As far as compute APIs goes, they are basically used to achieve general purpose computation using the GPU. So GPGPU is basically using GPUs for running arbitrary computations, which are traditionally handled by the CPU. So compute APIs, they kind of define interfaces that facilitate GPGPU. So before compute APIs, let's say scientists or neural network engineers, they were using graphics APIs to solve their non-graphics problems. And while that's possible, it's not ideal. So people have recognized that GPUs would be used for much more than graphics, and then they gave they gave us APIs to do this more easily. Some popular compute APIs are OpenGL, I already mentioned, CUDA API from NVIDIA, C++, AMP from Microsoft. But out of those, OpenGL is the most popular by far. So compute use cases, they include machine learning. So for example, training complex neural networks, it would take too long to do that on CPU in most cases, maybe even impossible. So image and video processing, many of the image and video processing algorithms are implemented using GPU. Cryptography, even weather forecast and climate research use GPU. There are much more of these. I didn't list them all. And now we are going to talk about the rendering pipeline. This is essentially a computer graphics primer. So in this slide, we'll see how rendering works on modern GPUs in a nutshell. Later, we will discuss this in more detail. So application provides or tells GPU what to render by specifying defined using meshes. Mesh is just an array of vertices in 3D space. So on top right part of the screen, you see a triangle, which is what we call a primitive in computer graphics. Other types of primitives are lines and points. And vertex is just a point, let's say, of that triangle, determines the position of one point of the triangle. So vertices are linked to form geometric primitives like triangles or lines, but also vertex can be a point, just a point. And then those meshes that application provides, they are animated each frame. So you see the rotating teapot. And then, of course, each vertex is positioned to the correct place on the screen. Then after that, after the geometry is processed, primitives are rasterized for coloring. So each primitive is tested against per pixel sample points, like you can see on the bottom right picture on the slide. And output color is computed for each hit pixel. And finally, color is stored in the frame buffer. Frame buffer is just a memory where data written out by the GPU is stored. So rendering is usually done in a double buffered fashion. So while GPU is rendering something to the back buffer, display controller is reading the front buffer and is basically rendering stuff, or not rendering, but sending stuff to the monitor. So once this is so, and then back buffer and front buffer are switched, and this is synced with the refresh rate of the monitor, so that to avoid flickering. So once monitor finishes refreshing the screen, these two buffers are switched, and then in next iteration, in the next refresh cycle, monitor will read a different second buffer while the GPU renders the previous one. Okay, so let's go into more detail in rendering pipeline. So it starts on the CPU. So application will provide a vertex input array, which basically contains per vertex data for each vertex of the object. In this example, it's only position and color of the vertex. So on bottom of the slide, you can see how this data might look like. So we have vertex 0, its position and color, which is red, then vertex 1 and vertex 2. And then this, along with the drawing commands, is sent to the GPU for rendering. The rendering starts with vertex shading. So shaders are basically application-defined programs that are executed by the GPU. Shaders, they are written in high-level shading language. For example, OpenGL has GLSL, and DirectX has AGLSL, which is high-level shading language. And vertex shader is run for every vertex. So in our example of drawing a simple triangle, a vertex shader is run for each of the 3 vertices. And it's important to know that each of these invocations of the vertex shader is independent. So remember SIMD, there is some set of operations that run on many different elements. This is essentially that. So on the right part of the slide, it's a simple shader. So on top of the shader, there is a pragma that defines version of the shading language to use. This is an indication to the compiler how to compile this shader, which features it can use, and so on. Then we define the read-only input attributes provided by the application. Those are the position and the color of the vertices. Then we define the write-only varying output, which is written by the vertex shader. We'll talk more about varyings a bit later because they are special. And then main function, like a C main. This is where the vertex execution, shader execution will start. And maybe the most important built-in variable in OpenGL is a GL underscore position. We have to assign that in the vertex shader, and it is a varying and defines the position of the vertex, and then it also defines the positions of the fragment, which we'll talk about later. Clipping. So after the geometry is processed by the vertex shader, some of this geometry might be positioned outside, or part of it might be positioned outside of something we call the viewing volume. So the viewing volume is the volume that defines visible area of the 3D space. So positions output by the vertex shader, we say that they are in clip space. Those positions are 4-component positions. So they have X, Y, and Z, 3D space, but they also have a W component, which we call a homogeneous coordinate. And it is this W coordinate that defines this viewing volume, as you can see on the illustration there. And the primitives are clipped against this viewing volume, and how that looks like in 2D is here. So this is just one plane of this viewing volume, and we have this yellow triangle. There it goes beyond the viewing volume. So what GPU will do, it'll kind of cut off the part that goes out of the viewing volume, and in this case it will create 2 new triangles, both of which are within the viewing volume. Now, why is this important? It's important for performance reasons. So GPU will essentially cut off all the geometry that is deemed not to be visible in the final rendering of the image. And in this way, we will save a lot of processing down the pipeline. So from that point on, those areas clipped off are no longer processed. Let's move on. Perspective divide. So if you think about it in real world, let's say if you have 2 houses of the same size, and one is close to you and the other one is far away, even though they are the same size, the one close to you seems bigger. It should be the same in computer graphics. So the clip space positions that are returned from the clipping from the previous stage, they are divided by this homogeneous coordinate W, and positions are now in a normalized device coordinate space, so-called NDC space. So what this division does is it basically gives perspective. So vertices with higher W value will appear further away. So on the bottom of the slide, you can see 3 triangles. They are all the same size, but they have different W values. So the first one has 1, second 2, and the third one has 3 for W. So you see how they are their size difference. So this is what gives perspective to objects in computer graphics. Let's move to viewport transformation. So after clipping and perspective division, all the vertices have coordinates in range -1 to 1 in X, Y, and Z dimension. These are called, that we said already, it's called NDC space, normalized device coordinate space. The window or viewport to which we render render to, usually will start from 0, 0 at the bottom left to W minus 1 or H minus 1 top right, where W and H are width and height of the window of viewport in pixels. So look at the bottom left of the slide. We have a kind of a triangle, that full screen triangle in the NDC space that spans from -1 to 1 and -1 to 1 in X and Y dimensions. The Z dimension is ignored there. So, however, the viewport or screen, it's not square, it's actually rectangle. So the width is 1350 pixels and the height is 778 pixels. So what viewport transformation will do, it will kind of scale and offset this triangle so that it's also full screen in the viewport. That's basically what viewport transformation does. Now we have to talk about winding order and phase culling. So winding order appear in window space. Winding order can be clockwise or counterclockwise. So the left triangle down there on the slide has vertices provided in a clockwise order, as you can see. The right one has vertices provided in a counterclockwise fashion. But why do we care? Why is this important? It's important because triangles with counterclockwise vertex order are considered front-facing, and those with clockwise vertex order are back-facing. This can be changed, so this is configurable, but by default it's usually like that. So back-facing triangles are often culled, so it means discarded, as they are hidden by a front-facing triangle. So look at those two boxes, rotating boxes. So the left one has culling disabled, and you can see that those faces of the box that are actually shouldn't be visible, they are hidden, they are still rendered because culling is disabled. The right box has culling enabled, and those faces are not drawn. So why is it important? Again, performance reasons. We don't want to draw something that is then hidden. That's just waste of GPU resources. So, well, in most realistic applications, culling is enabled, and these hidden faces are thrown away, culled. Okay, so now we come to rasterization. What is rasterization? Rasterization basically determines which fragments, so fragments are potential pixels, which fragments might be covered by the primitive, like a triangular line. So screen, or actually window coordinates, are used in this test. And the fragment is considered to be covered by a primitive if its center is covered by the primitive. So look at the illustration on the left here. We have like a 8 by 8 viewport, and you can see a kind of blue triangle there. After rasterization, rasterizer will decide which fragments are covered by this bluish triangle. So you see that only the fragments where their center is kind of covered by the triangles are actually considered to be covered. And then rasterizer will also generate a fragment thread for each of those covered fragments, which brings us to well, actually, sorry, I still have to talk about the wiring interpolation. So I said when we were discussing vertex shader, I said that the vertex shader outputs are called varings. So here you can see the part of the vertex shader where this is defined. The varying is called color out. So what happens in the fragment shader is that those outputs of the vertex shader are interpolated for each rasterized fragment. And this interpolation is done during the fragment shading. So each fragment shading location will calculate its own interpolated varings. And this color kind of colorful triangle to the left, it shows how this interpolation is done. So there's a fragment there. And this is how we calculate, how GPU will calculate the interpolated color out, varying for this fragment. So one thing to remember is that this interpolation, the varying interpolation, is perspective correct. So these two images on bottom right part of the slide, they show what happens when the varying interpolation is not perspectively correct and when it's correct. So what happens is that texture coordinates are passed from vertex shader to the fragment shader, and they are incorrectly interpolated. So they're not perspectively correct in interpolation. And see what happens when we try to sample the texture in fragment shader. There's some kind of skew. However, when it is perspectively correct, the texture sampling will look correct on the right there, and the texture mapping then will produce correct result. Let's move to fragment shading. So each of those rasterized fragments, for each of them, fragment shading is run. Just like vertex shading is run for every vertex, fragment shading is run for every fragment. Again, each invocation of a fragment shader is independent. Again, think single instruction, multiple data. Fragment shader has access to texturing functions, so how to sample the textures, as well as the discard command. So the discard command called in the fragment shader will ensure that all outputs from the fragment shader are basically ignored. Fragment shader can output multiple color values. This is called MRTs, or multiple render targets. We'll not talk more about this in this presentation. And can write out a single depth value and also a stencil value. I didn't write that there. So depth and stencil value. Okay, so you see this so color in. That's basically a user-defined fragment input that matches the color out varying that was specified in the vertex shader. And this is like we explained, it's interpolated for each fragment. Then this is user-defined output. It's potentially written to frame buffer color attachment 0. This just means that it's written to this to those. So as far as for the depth goes, this fragment shader outputs depth computed as part of the vertex processing. So it's in this case it comes from the Viewport transformation. So it's a Windows space set coordinate. Also note that fragment shader can explicitly write depth by using the GL_frag depth built-in, which is then written out of the frame buffer. That's essentially fragment shading. So it allows us to control how the fragment outputs are computed, and what kind of color and depth and stencil values are written out of the frame buffer. So depth test. It's basically a fragment operation that runs after the fragment shading. Sometimes it can run before, which is called an early depth test, but we'll not talk more about that in this presentation. So the fragment's output depth is compared with the depth value for the given sample or fragment in the frame buffer. If the depth test fails, fragment is discarded, so its outputs are ignored. If test passes, the depth buffer is updated with the fragment's depth, unless depth writes are turned off, which can be configured. So on the bottom left of the slide, so we have two triangles. Red triangle is drawn first, and it has depth value which is lower than the depth of green triangle that is drawn second. However, because depth test is disabled, green triangle will overwrite the red triangle in the frame buffer, even though red triangle is closer to the camera, closer to the viewer. On the right, depth test is enabled, and then you see what happens. So because we selected, in this example, we selected a depth function to be less or equal than, GPU will compare the depth of the green triangle with the depth of the red triangle, which is in the frame buffer, and we'll figure out that the depth of red triangle is smaller, so we'll not draw a green triangle over the red triangle. So essentially, depth test allows us to render realistically, like in real world. Objects that are further away will be hidden by objects in front or closer to you. Next is color blending. So color blending gives us a way fragment color outputs from the fragment shader. It can only works with the colors. You cannot blend the depth buffers, for instance. Blending happens according to the user specified blending function. An alpha component, color component, is often used in this blending computation. So again, bottom left part of the slide, there is a blending disabled. So green triangle, which is drawn second, simply overwrites the red triangle in the frame buffer. On the right, we have blending enabled, and we used this blending function. I'm not going into details about the equation itself. It's usually used to achieve transparency. So what happens is that basically the value of the green triangle is combined with the color in the frame buffer, and that's the result. You see, red triangle is shown under the green triangle. Okay, so, and final stage, not stage, just a piece of memory, right? The frame buffer. So after all this processing, data is stored into the frame buffer. So frame buffer contains a per pixel color value, or multiple values per pixel if MRT is used, multiple random targets. Application, of course, can blend colors produced by the fragment shader with those in the frame buffer, like we just explained. Then it also has a per pixel depth buffer, which stores the depth of the fragment. So this is basically a distance from the pixel to the viewpoint, which allows us to keep track which objects are further away and which are closer to the camera. An application can select the depth test function, of course, and a per pixel. So frame buffer also has a per pixel stencil buffer. So I didn't talk about this buffer a lot. I just mentioned it, but it can be very useful while implementing certain types of algorithms. Like, for instance, in games, reflections can be implemented using with the help of a stencil buffer. So on the right half of the slide, we see how this fragment processing will work. So rasterizer will decide which fragments are covered, which are then fragment shaded. Fragment operations are then run, like depth testing and blending, and then the color and depth and stencil, they are written into the frame buffer. And now we'll do a short recap of the OpenGL rendering pipeline. So, like I said before, the first part runs on CPU. It's preparing the meshes of vertices and uniform data for the objects that we want to draw on the scene. Vertex shading runs next, so for each vertex. Primitive assembly does just a name for clipping, perspective, divide, viewport transformation, and phase culling, all of which we talked about. Rasterization will determine which fragments are covered by the primitives. Fragment shading, again, for every covered fragment, computes color value or values and depth for every rasterized fragment. Fragment operations, so they run per sample. So like depth stencil tests and blending. And finally, the data, the color depth stencil are written into the frame buffer. I've omitted a few parts of the pipeline. So there are also compute shading, which is kind of an isolated stage that is not part of this graphics part of the API, OpenGL. It runs compute shaders, and I also omitted tessellation and geometry shading, but what I showed you is the core of the OpenGL rendering pipeline. So let's do a summary of GPU use cases. So graphical use cases, the main ones, of course, are user interfaces. Nowadays, UIs are very complex, and most UI rendering is GPU accelerated. So then multimedia integration, so video and camera capture and processing, also done with GPU. Of course, gaming, desktop and mobile, virtual reality and augmented reality, all of that could not exist without GPUs. As far as compute use cases, we talked about this, but we can repeat it. So machine learning, so for example, training neural networks uses GPUs a lot. Image video processing algorithms, cryptography, weather forecasting, climate research, all of that use GPU. Unfortunately, I cannot go into details into any of these compute use case applications because there is not enough time. But I encourage you to look into them yourself. Okay, so we are done with the technical part of the presentation. There's a bit later more about Arm Mali, but we are mainly done. I would like to talk to you now about the engineering roles in a GPU organization. So those are individuals who design and build GPUs, like myself and my colleagues at Arm. So GPU ecosystem, it's very wide and spans everything from games and game engines on one end to GPU hardware on the other end. So because of its size, I can imagine that many types of engineers are needed to design a good, successful GPU. So ecosystem, of course, on top, it's software that uses the GPU, like computer games, game engines, then GPGPU applications, VR, AR, automotive applications, and so on. Then the next layer is a graphics API, like we said, graphics and compute APIs. So they define the interfaces that those applications on top will use to speak with the GPU. Then next layer, one layer lower, is of course operating systems, which runs the GPU driver, and shader compiler, which compiles the GPU programs, shaders. Shader compiler is part of the GPU driver, is just shown there for clarity. And of course, on the bottom there is a GPU processing unit hardware, which actually runs shaders and does everything basically. So let's first we'll talk about the GPU driver engineer position. So driver engineers implement the graphics like OpenGL or compute like OpenCL API for the GPU hardware. So driver engineer is a kind of a central role in a GPU organization, and it touches on most areas of GPU development. Oh, sorry. So driver engineers, they will know ins and outs of APIs they implement. And of course, because they're working with the GPU drivers, this is the main point of concern for driver engineers. They will know everything there is to know about GPU drivers. As for shader compiler, so driver engineers will have good understanding of the compiler and the GPU ISA, which is instruction set architecture, but they will not go into compiler implementation. This is the job of compiler engineers. As for the GPU hardware, we'll have a very good understanding of GPU architecture, but won't go into hardware design details. That's for the hardware engineers. As for the software model, which is a software model of the GPU hardware, driver engineers will use GPU software model for driver implementation and testing. As far as external GPU users go, driver engineers are occasionally asked to assist with issues faced by external users. For example, game engineer lover will hit some bug, will often help them investigate why, what's going on, whether it's their issue or driver or hardware issue maybe. So like you know, I'm a driver engineer, so I will tell you a bit more about what I do as well. So in my own role, I work on design and implementation of the GPU driver stack for future, so upcoming Arm Mali GPUs. My responsibilities include evolving the driver stack for the upcoming GPU hardware architecture, analyzing and implementing driver support for new GPU hardware features. Then I will also often analyze various driver areas that might need to be improved and design and propose those solutions for various reasons, improvement for various reasons, performance and whatnot. I will implement also Vulkan API features for the future Arm Mali GPUs. And also I will often, because I work in this team that works with future GPUs, I will often support hardware engineers with investigating and resolving GPU hardware issues that are found during the GPU development. So my role requires excellent understanding of the graphics APIs, especially Vulkan, and to some degree OpenGL. Of course, the driver stack, I have to know it ins and outs of it. Then GPU architecture, as well as system architecture, so the CPU, GPU memory, as well as good understanding of our shader compiler and the GPU software model. That is in a nutshell. Let's go to the compiler engineer role. So compiler engineers, they implement the shader compiler that translates shaders written in high-level shading language such as GLSL to executables executed by the GPU hardware. Compiler engineers will have excellent understanding of the shading language that they implement the compiler for. They have a good grasp of the GPU driver, but they won't go into implementation details. That's our job. Shader compiler, of course, that's the main point of concern for compiler engineers, so they know all about it. As for the GPU hardware, they will have excellent understanding of GPU instruction set architecture because this is what they compile for. GPU software model, like driver engineers, compiler engineers use the software model to test compiler during the implementation and implement new features. And they will often, or maybe occasionally, be asked to assist with issues that external users face, because users often think that our compiler is to be blamed for some issues that they face. PPA engineer. So this is PPA means power performance area. It's a very interesting position. These engineers analyze the GPU performance with regards to real-world content, like some games. And they assist GPU hardware architects with finding improvement opportunities. So PPA engineers, they will have very good understanding of the APIs, decent grasp of the GPU driver. They will know the details, but they will know the overall picture. They have good grasp of GPU ISA and shader compiler. They will have good understanding of GPU hardware at behavioral level. Then they will use software model like the driver engineers but in their case they use it for performance analysis. So basically all performance analysis is done, or most of it is done using the GPU software model, and only if we see that some hardware feature could improve the performance and will improve performance, then we will implement in the hardware. And they will work with external software content, because what drives hardware development, at least GPU development, is external content like games, right? If we know that something will improve, some feature will lift the FPS of the game by 20%, we might implement that in our GPU. GPU modeling engineers, so these are engineers that implement software model for the GPU hardware. This model it's very important component in this whole ecosystem, because this model is then used by various teams, by driver, engineers, compiler, PPA, even hardware for the verification, for implementation and testing. So the main areas where GPU modeling engineers will work in, basically they will have a good understanding of the GPU ISA. They'll have very good, excellent understanding of GPU hardware architecture, and of course they work with the software model, so this is they know ins and outs of it. Very important position. So hardware design engineer. Well, these engineers, they are the ones who actually design the hardware, right? Using the RTL design methodology and the HDL language, like Verilog system Verilog. So GPU hardware is a really complex piece of hardware. And then because of that, we have multiple teams that focus on various modules of the GPU hardware, like, for instance, memory subsystem or shader core, texture mapper, and so on and so on. There are many of them. So hardware engineers, of course, the main focus of their work is the designing the GPU hardware. They have excellent understanding of the GPU architecture, and they know ins and outs of the hardware modules that they design. Like I mentioned, they will use a GPU model for the text case generation and verification. And the last position I will talk about is the hardware verification engineer. So this is also hardware engineer, of course. They apply formal verification methodology to GPU hardware verification. These are the guys that make sure that hardware behaves as it was designed. There are also usually multiple hardware verification teams, although fewer than the hardware design. For instance, we can have top-level hardware verification engineers that will look at the GPU as a kind of a box, and will verification engineers that will test, let's say, texture mapper or memory subsystem. Again, hardware verification engineers, they will have excellent understanding of GPU architecture, and they will know the details of the hardware module they verify, and to use GPU software model for their text case generation and verification. So they'll compare the output of the model with the output of the actual hardware and see if there are some differences and why they are different and so on. Okay, so as for GPU engineering roles at ARM, we are constantly searching for engineers to join our team. So the roles span from entry level to experienced professional positions. I included a link there that you can where you can check what roles are available. So if you're looking for software engineering roles, please select software engineering, the job category. If you want to look at the hardware engineering roles, select hardware engineering in the job category. I encourage you to look at the roles because, well, in my opinion, all of them are very interesting. Last part of the presentation. I have to pick up the pace because we're running out of time. Arm Mali. This is ARM's GPU for mobile and embedded market. It's what me and my colleagues are designing and building. So very quickly, desktop GPUs, their architecture is what we call immediate mode GPU architecture. So the way that works is that geometry, so the transformed by the vertex shaders, is stored in a FIFO within the GPU. You can see that on the left diagram on the left side of the slide. And then this geometry is fragment shaded, of course, and there's no need to read this geometry from the main memory because it's within the GPU in this FIFO. So advantage, of course, is that very little external memory bandwidth is used for storing and retrieving in the intermediate geometry data, because most of it is in the fast access FIFO within the GPU. There are disadvantages, however. Primitives, GPU must process the primitives, like let's say triangles, in the draw order. So if you draw triangle 1 followed by triangle 2, GPU have to process them in that order, right? Which means that each primitive triangle may cover any part of the screen. So what can happen, and often happens, is that fragment shading can jump around the frame buffer, which means that every fragment might need off-chip external memory access for blending, color blending, depth test, tensor test. And this can lead to extremely high external bandwidth for high resolution frame buffers, right? And this in turn leads to high power consumption. So, for example, NVIDIA's modern NVIDIA's GPUs, their power budget is maybe 60 or 70 watts. Is huge. Compare that with maximum of 2 watts that mobile GPUs can use. So this is like 30 or 40 times bigger power budget. So because of that, mobile GPUs, which Arm is one of, use a different approach. So Arm Mali is a tile-based GPU. So the way it works is that it splits the screen into smaller regions called tiles. So in this example, on the left upper part of the screen, you can see that the screen is divided into 16 tiles. That's just arbitrary for this example. And then what happens is basically rendering is divided in 2 parts, like you can see in the pseudo rendering algorithm. The geometry pass will basically go through each draw call in the render pass, and then for each primitive in that draw, it will run vertex shading. And then if the primitive is not culled, it will append it to the tile list. Tile list, it just keeps track of the primitives that basically affect that tile. And then the second pass is fragment pass, and then for each tile in the render pass, and then for each primitive in the fragment shading is run. So why do this? The advantages of this approach is that external bandwidth reduction, of course, is the main advantage. All frame buffer data, so color depth and stencil for a tile, is stored in on chip in a fast access memory, so within GPU. And tile is fully fragment shaded before it is written out to external memory. And once it's written out, it's never read back. At least not during the current rendering. Various optimizations are possible here in this scheme. For instance, if we know that depth and stencil data is only used in rendering, not after, we don't have to write it out to the external memory. Then we can use something that's called transactional elimination, and so on and so on. Of course, there are disadvantages. GPU, it must store vertex varying data, so in tiler state, to basically the product of the vertex shading or geometry stage. It has to write it to external RAM, which is then read by the fragment pass. So a balance must be struck between this extra bandwidth in geometry and bandwidth savings from frame buffer data. However, I mean, it turns out that this approach works much better for embedded GPUs, because it allows us to design reasonably efficient GPUs that use way less power than the desktop GPUs. Okay, so quickly, Mali architecture. This is a unified shader core architecture, which means that a single shader processor executes all shader types, or compute shaders, vertex shaders, and fragment shaders, all run by the same hardware. Users or silicon partners, they can configure a number of cores within the GPU. L2 cache shared between all shader cores, which reduces external bandwidth. We have 2 parallel issue queues in our GPU, so one for the compute and vertex work, and the other for fragment, so that we can increase the throughput. Yeah, and also distribute the workload across all available shader cores. Okay, so this is a Mali shader core. So basically, execution engine that you can see here on the diagram, it's basically that's what executes shader instructions. Threads, like we talked before, threads are packed into warps before executed in parallel by GPU. In this generation of Mali GPUs, warps are either 4 or 8 threads, depending on the way the hardware is configured. Low store unit, of course, is responsible for all shader memory accesses, but is not related to texture sampling. And low store unit allows access to a 64-byte cache line per clock cycle. Wiring unit implements fixed function wiring interpolation. We talked about wiring interpolation. Texture unit handles all memory accesses related to texture sample. So when you sample a texture, this unit will be used. Let's move forward. So recap of our GPU. Like we said, our Mali GPUs are based on the principle of tile-based rendering. So our Mali is designed to improve system-wide energy efficiency by minimizing external DRAM bandwidth for the frame buffer access, which of course will reduce power consumption. Our GPU support Vulkan, OpenGL ES, and OpenCL APIs. If you want to learn more about our Mali, and I suggest, well, I hope you will want to, these are some links that you can weigh. Our Mali, if you wonder what Mali stands for, it is not some Norwegian word. It's actually, it comes from a Slavic word, Mali, which means small. So yeah, it's from Slavic language. So a summary, basically a summary of the whole presentation. So we discussed quite a few things throughout the presentation, such as GPU architecture, rendering pipeline, GPU APIs, and GPU engineering roles, and in the end, Arm Mali. So there are a few key points I would like you to take away from this presentation. First of all, GPUs are everywhere. They have outgrown their computer graphics use case and now empower scientific research via GPGPU, artificial intelligence, autonomous driving, and much more. This means that GPUs will become more important, and consequently, engineers with GPU knowledge are becoming more and more sought after. Our discussion of the GPU engineering roles made it clear that designing a GPU requires bringing engineers from both hardware is challenging and very interesting at the same time, and it's a career worth pursuing for both hardware and software engineers, in my opinion. And finally, Arm Mali now empowers 1 billion devices, more than 1 billion devices, and we are always searching for qualified, curious, and knowledgeable and knowledge-hungry engineers to join the Arm Mali team. So if at any point in time you will consider working for Arm, and especially within the Arm Mali team, I encourage you to reach out to me, and we can discuss the best way forward. So I guess this is the end, and we are now doing a Q&A, I think. Ivana? Hello, Ivana? Oh, I'm not sure if Ivana can hear me, but yeah, I will wait. Ivana u stvari ja ne čujem Ivanu na Zoomu, pa mislim da ćemo pričekati. Oh, I think I said that in Bosnian. Oh, we have a question from Riyadh. I'll read the question. Are there any versions of Arm Mali GPU which are used in embedded applications? So depends what do you mean by embedded applications? I mean, mobile phone is a kind of embedded system. So we have our Arm Mali is used in phones, TVs, and automotive industry so far, so cars. So those are the three main users of Arm Mali GPUs. Oh, sorry, I haven't seen the question from Emin. Okay, I'll read it. Were you in any way affected by 2017-18 Bitcoin mania that caused shortage of GPUs? Not that I know. I mean, I think that desktop GPUs are mainly used for mining. Because they are more powerful than the mobile embedded GPU. So I don't think we had any issues with that. Okay. So Ivana is having some troubles with the microphone, so I think this is it. So thanks everyone who joined. I hope you got something from this presentation. And again, if at any point, well, let's just say if you want to learn more about GPUs and you need somebody to help point you in the right direction, feel free to reach out. I provided an email here and also LinkedIn profile. And if you are a young engineer, so graduate or a student looking perhaps to pursue a career in GPU engineering, reach out to me, and I will try and help. Thank you very much.